We've seen some of the ways in which matrix arithmetic is similar to ordinary arithmetic with real or complex numbers. One property that real and complex numbers have is that if you give me any non-zero number x, then it has a multiplicative inverse. That means a number 1 over x, such that when you multiply x and 1 over x, you always get 1. In this video, we're going to investigate a similar property for matrices, but we'll find that actually not every non-zero matrix has a multiplicative inverse. Here's the definition of an invertible matrix. An n by n matrix A is called invertible if and only if there exists a matrix B such that A times B and B times A are both equal to the identity matrix. Now if such a matrix B exists, then there's only one such matrix, because if A times B and B times A, and A times C and C times A are both equal to the identity, then we can do the following calculation. B is equal to B times the identity. That's a fundamental property of multiplying by the identity matrix. But the identity is supposed to be equal to A times C, amongst other things. So I can substitute A times C for the identity to get B times A times C. Since matrix multiplication is associative, I could rewrite this as B times A times C. But again, B times A is supposed to be the identity. So this is the identity times C, which is just C again. We've shown B is equal to C, so if there is a matrix which has this property, then there is only one matrix with that property. A matrix B such that A times B and B times A are equal to the identity is called an inverse of A, or sometimes a multiplicative inverse of A. We write A to the power minus 1 to denote that inverse. You've probably seen this result for 2 by 2 matrices, which tells you exactly when a 2 by 2 matrix is invertible. The 2 by 2 matrix ABCD is invertible if and only if A times D minus B times C is not equal to 0, and in that case you can even give a formula for its inverse. The inverse matrix A is equal to 1 over AD minus BC, scalar multiplied into D minus B minus CA. As an example, if you take the matrix A to be 1, 2, 3, 4, then 1 times 4 minus 2 times 3 is not 0, so it is invertible, and its inverse is 1 divided by 1 times 4 minus 2 times 3, scalar multiplied into 4 minus 3 minus 2, 1. On the other hand, this would provide us with examples of non-zero 2 by 2 matrices which nevertheless were not invertible. For example, if you took 1, 1, 1, 1, well, 1 times 1 minus 1 times 1 is 0, so this is not invertible. You can see that multiplicative inverses for matrices are going to be more complicated than multiplicative inverses for ordinary numbers, because there are non-zero matrices which do not have inverses. Let's look at a sufficient condition for an arbitrary n by n matrix not to be invertible. What this theorem says is that if you have an n by n matrix with a row of zeros, or a column of zeros, so every entry in a particular row or every entry in a particular column is 0, then that matrix is not invertible. Let's do the proof of this. So let's suppose every entry in the pth row of A is 0. And if we write, as usual, A to be the matrix whose ij entry is A subscript ij, then the entries in the pth row are AP1, AP2, up to APn, and we're assuming that those entries are 0. The way we're going to show that A is not invertible is by showing that if for any matrix B, A times B cannot be the identity. So that means A cannot have an inverse, because if it did have an inverse, then when you multiplied it on the right by that inverse, you would get the identity. So our aim is to prove that no matter what matrix B you take, A times B is never equal to the identity matrix. So let's investigate the product A times B. We know what its entries look like. In fact, we have an expression for them. The ij entry of A times B is equal to Cij, where Cij is the sum from k equals 1 to n of Aik times Ckj. So let's examine the pth row of A times B. Well, what happens on that pth row? That pth row consists of the entries CP1, CP2, and so on. So let's just look at an arbitrary entry CPJ in the pth row of A times B. By definition, that's the sum from k equals 1 to n of apk times bkj. But all of those things apk are 0. That means the whole sum is 0. So we've shown every entry in the pth row of AB is equal to 0, and in particular AB is not equal to the identity no matter what B was. If A has a column of zeros, then you can do a very similar argument to show that BA would always have a column of zeros. So again, a matrix which has a column of zeros cannot be the identity matrix, and therefore a matrix A with a column of zeros is not invertible. Finally, let's just make an observation about inverses of products of invertible matrices. Just like for permutations, and just like for invertible functions, if you have matrices A1 up to AN, and they're invertible, and they all have the same size, then their product, A1 times A2 times A3 up to AN, is invertible, and its inverse is obtained by multiplying the inverses in the opposite order. For example, if you had two invertible matrices A1 and A2, if they are invertible, then their inverse is A2 to the minus 1, A1 to the minus 1. And you can check that very easily. Like, it's the same proof that we did for compositions of functions. It's the same proof that you might use for permutations. You just check that the product of A1, A2 with this thing really is the identity, but that's nice and easy. A1 times A2 times A2 to the minus 1 times A1 to the minus 1. I don't have to put any brackets because I know that matrix multiplication is associative, so I can just cancel out this thing in the middle because it's the identity. Multiplying by the identity doesn't change anything. So I've just got A1 times A1 to the minus 1, and of course that is the identity of whatever appropriate size. And similarly, if we do the multiplication the other way round, A2 to the minus 1, A1 to the minus 1, A1, A2, precisely the same thing happens. Because matrix multiplication is associative, I can bracket this anywhere I like. So I choose to do the inner multiplication first, and that gives me A2 to the minus 1 times the identity times A2, but multiplying by the identity doesn't do anything, so I've just got A2 to the minus 1 times A2, and of course that is, again, the appropriate size identity. So very often, if we haven't specified the size of a matrix, we'll just write I to refer to the identity matrix of whatever appropriate size.